Hi everyone, I'm Dr. Jeremiah Blanchard, and in this video we'll briefly go over the fundamentals of the Rust language. This video is focused in particular on how Rust is different from other systems languages. It's intended for folks who have already had at least some programming experience in C, C++, or a similar language. Additionally, I want to note that we'll be talking about the language, but not the extensive ecosystem of Rust, in particular tools like Cargo. The Rust language is different and unique enough that I'm going to stick with the basic Rust compiler, leaving Cargo and related tools for a later discussion. So with that, let's jump right in. If you've heard of Rust, you may be wondering, why yet another language? We already have C, C++, and dozens of others. What's so special about it? And indeed, Rust is a C-family language with syntax that will be very familiar to you if you've worked with its siblings, with typical operators, curly braces for code blocks, double-quoted strings, and the like. Here we can see a main function declaration. We print hello Rusty world, and then we define a variable alpha. After that, we assign beta to the value of alpha, then we set beta equal to alpha plus beta, and then we print them out. There are little differences here and there from other C-family languages, but nothing huge. It's mostly variations on punctuation and symbols. If you've ever worked with a typical C or C++ compiler, the compiler command line will look very familiar to you as well. Here we compile the hello.rs file, the extension for Rust, and we tell the compiler to produce an executable named hello. When we execute it, it prints out the statements as we would expect, with the values of 5 and 10. With that said, there are some differences, particularly with more complex types. If we try something similar with strings, create a value in alpha, then assign beta to that value, and then we try to print them, we'll get a compiler error. This is because Rust integrates a system of ownership and the borrow checker, which we'll get into later, which makes certain classes of memory errors impossible by virtue of syntax and catchable at compile time instead of requiring runtime checks. Okay, so let's dig into an example a little bit more. First, we'll create the alpha identifier. By default, Rust types are immutable, that is, unchangeable, and so that's the type that alpha will be. We'll set it, but we won't be able to change the value after that. Now, optionally, we could define the data type as well, but Rust is smart enough to use the assignment queues to set the type here to a string. The string object has a few constructors, and this particular one will build an object from a literal. When a value is constructed, some identifier will own it, and that will define its scope unless it's moved. So in this case, alpha owns the string object, holding the important message. Immediately after, though, we assign beta to alpha. The default behavior for assignment is to move the value, that is, change its ownership. So now beta owns the string, and alpha is no longer valid. If we just print beta, that's no problem. Println, by the way, is a Rust macro. These work the same way as they do in C or C++ for the most part. They're sort of a search and replace construct. Many simple procedures that do not consume values can be effectively defined as macros to avoid transfers of ownership, but we'll get into that a little bit more later. Suffice it to say, macros are pretty common in Rust, particularly when the values aren't being modified. An issue comes in if, after the assignment, we try to print alpha. Alpha is no longer valid. It has no value, so the compiler will object. And this is the crucial difference between an ownership error, which is caught at compile time, and an invalid pointer, which would only be caught at runtime. In Rust, a large number of these errors will become compiler errors, and that makes them impossible to find their way into deployed software. But wait, we had that integer example. Why did that one work? The critical difference here is Rust's copy trait. This trait indicates that a type can be copied bit for bit and work as expected. For most complex types, including strings, this isn't true because they have pointers or references, which means this sort of shallow copy won't work properly on its own. However, for very simple fixed-length types, like numbers and characters, a deep copy isn't necessary. In this example, as before, we print a greeting to the screen, then create a value, 42 in this case, owned by alpha. However, when beta is assigned to alpha, because integer types have the copy trait, the value is copied and beta owns the new value instead. As a result, we can access and use both alpha and beta after the assignment. It's critical to note that if the copy trait is enabled on a type, the copy operation is not defined by code. It's a function of the language itself. As a result, it should never be applied to types with pointers or references of any kind. While the syntax of Rust is probably not surprising to you if you're coming from a C-family language, it's worth reviewing a few elements for clarity. Additionally, we're going to go through an example of a value being passed via borrowing, and with transferring ownership via function calls, so that we can start to understand how these values move around practically. In this case, we're going to read from the standard input, and to do that, we'll want to use the standard I/O module. In Rust, the use keyword allows us to import modules. We'll also trace progress of the stack and heap here, so let's add the main stack frame. Within the main function, you can see that we print unsubscribe to the screen, then create an identifier A and assign it to the value that getName returns. Here, getName is a bona fide function, not a macro. This one is pretty simple, thankfully. We'll see right away that Rust uses the arrow notation to define the return type, which is string in this case. Within this function, we see an example of a mutable variable, which uses the keyword mut or mute as a designation. This allows the value to be changed later. You'll also see we're calling another string constructor, new, which creates an empty string object that the name variable owns. Next, we'll print out a prompt, and then we'll call the readLine method to read from the standard input. We have to provide a place to store whatever is read from the input, so we can pass a mutable reference to the name variable. References are used in Rust to allow borrowing of a value. In this case, the borrowed value can be changed. This is necessary because the default is for those values to be immutable. The readLine method borrows the value as buff. If the user types Garrett, that will be stored in our string object. When readLine terminates, its borrowed reference falls out of scope, and then getName's return statement is reached. A returned value is moved to the caller. Its ownership is transferred, so that the string is now owned by the A identifier. The same process is repeated for B. GetName is called, creates a string object, it invokes readLine. The user enters characters, and those are written to the string object. GetName then returns the string, whose ownership is transferred to B. Comparisons in Rust are similar to those in C, C++, and Java, but with one key difference. They do not require parentheses around the comparison itself. Here we compare two values, and if they are the same, we print out why are there two, and then the value of A, in this case, Garrett's. When the main function ends, the stack frame is released. All the values owned by the stack variables fall out of scope and thus are cleaned up, and that includes both of our strings. Finally, the program terminates and the heap and stack themselves are reclaimed. While all of this works fine, if we compile this code, we'll get a warning. The compiler will complain about an unused result value. So why is this happening? Well, as we've discussed, Rust does a good job of eliminating certain classes of errors. This is because Rust was designed with security and concurrency in mind. As a result, the Rust standard library has checks for, well, almost everything. Many functions return a result value, and if you don't catch it, the compiler will complain. Let's take a look at a similar but slightly modified example. Here we call getMessage and catch the value in the message identifier. The getMessage function will create the input variable and print a prompt at the screen. For good measure, we may want to flush the standard output to make sure everything is on screen and nothing is in the buffer. When we call the flush method, it returns a result value. A result holds any returned value, if there was one, and also an error value in the case that there was an error. This is what the compiler was complaining about us not handling before. An easy way to silence the compiler is to call the results unwrap function, which essentially assumes that there is no error and continues. Now this can be dangerous, and it should only be used when you're certain that either the error is impossible or that it would be of no consequence. Here, the worst case scenario is that the screen buffer is not flushed, so we decide it's okay to ignore any error. Next, when we call readLine, we invoke the expect method on the result. This method will do nothing if there is no error, it simply returns. However, if there is an error, it will terminate the program with the message passed in as its final communication. Once we're past that, as in the previous examples, we move the value back to the main function. In this case, we're using a string pattern. We're embedding a variable name into a string in order to print it, which is one of those nice features integrated into Rust. And as a result, our message is printed with the correct formatting. Another construct that we'll see a lot in Rust is the for-each construct, i.e. an iterator-based for loop. In this code, we see our first example of a comment, in this case a line comment, which as in C, C++, Java, and related languages, indicates that the rest of the line is a comment. This is followed by our exclamation of delight in potatoes, printed at the screen of course, after which we proceed to count potatoes using a for-each loop. We also see an example of a block comment, again just like C family siblings. Here the iterator value is named potato number. As with other variables, it does not require a type, as this can be inferred. The iteration is defined by an integer range. As in most languages, the range indicates the starting point and the end condition, not the final value to use for the loop body. Because the end condition is 4, the body of the loop will be executed for values 1, 2, and 3. In this case, the body is simply a print statement, so it prints 1 potato, 2 potato, 3 potato. While this example in particular uses an integer range, the for each loop can also work with other iterable types, such as those in the standard library. As we noted before, Rust moves values by default, but it allows borrowing via references. With that said, Rust designers were also concerned about concurrency, so there are some additional rules about borrowing. Critically, there are 2 major types of references, mutable and immutable. In our first example, we create a string, mytastyburger, with the value cheeseburger. Then we create another variable, iCanHasPlease, but we assign it as a reference to the first variable, i.e. it is borrowing the value. We then call the printBorrowed function, passing the value as a reference, which is, of course, borrowed. This prints the value that was borrowed. Finally, we print out the original variable's value as well as the value borrowed by iCanHas, and all of these values are the same in this case. As we can see, there's no problem with having multiple borrows occurring at the same time. Well, at least that's true for immutable references. When it comes to mutable borrows, there can be only one. If we create a mutable variable, OG, then we might create our first mutable reference variable, borrow1. We could try to create a second mutable borrow, borrow2, and then print all of them out. However, if we compile this code, we'll find that the compiler terminates, telling us that the OG-owned value cannot be borrowed more than once via mutable reference. Now that we've talked at some length about borrowing values and ownership, it's worth looking at the types that are built into the Rust language itself. Perhaps not surprisingly, we find most of the types that we are familiar with here. Various widths of integers up to 128-bit, with signed and unsigned variants, for example. There are also the expected floating point and character types, as well as Boolean values and arrays. As you might expect, Rust's bool type can only have values of true or false. One type you may not have seen before is the tuple type, and it allows us to bind a finite number of values together. As we'll see momentarily, tuples can be particularly useful when we need to return or otherwise capture multiple values. Okay, so how does this tuple type provide a mechanism to return multiple values? Well, in our example, we'll create a string holding the value Riker. We'll then invoke the dupeName function, passing in the name variable. Note that we are assigning 2 new variables, number1 and number2, surrounded by parentheses, to the return value. This is a tuple assignment. It allows us to assign multiple variables to the individual values stored in a tuple. Because we are not passing a reference to name, its value will be transferred to the dupeName parameter. Looking over to the function, we see that its return value is a tuple composed of 2 strings. Within the function itself, the first variable is assigned a value for a new type of object, a vector, also known as an array list. We also have a for loop which we use to store values in the vector. Here, we're using the clone method, which creates a deep copy, to duplicate the original string twice, storing the new values in the vector. Finally, we return a value. In this case, we create a new tuple from the items we pop from the vector. We print those values to the screen, and then the program ends. It's worth keeping in mind that Rust vectors are designed similar to the C++ vectors. They're essentially arrays with dynamic resizing mechanisms. This makes them a very low-cost abstraction. A nice feature of Rust missing from most systems languages, but present in many scripting languages, is the ability to access slices of an array or string. Our example starts with the allocation of a string, hello world. We'll also put the string's characters to the right, along with each character's index. Here we create a variable, slicey, that goes from the beginning of the string and terminates before the 5th character. It is a slice reference. It does not own the memory, but is borrowing a section of it. We can also see the range to the right. Our second slice, dicey, will go from the 1st character, again ending before the 5th character. And our third slice, chicken spicy, will go from the 6th character to the end of the string. We can then print each of these slices. The result is that each subsection of the string appears on the screen. One interesting feature of Rust is that all string literals are in fact string slices, or the str type. This type is much more limited than the full string type, but that also means that there are many optimizations that can be done by the compiler for this type. We've noted that in many ways, Rust helps avoid various classes of errors, but the reality is that sometimes we need to access raw data on the machine. either because there's no other way to access the appropriate information, for example, accessing specific locations in memory, or because it would be onerous and slow to do so within the borrow checking framework, for example, graphics operations. For this reason, Rust has a mechanism to disable checks and use raw pointers via what are referred to as unsafe blocks. In our first example, we start by creating an integer value. Just after, we create two new and unique values. First, we borrow a reference to our value, but we do so as a constant raw pointer. In other words, the data cannot be changed, but we do have access to the raw memory address. Note that this in and of itself is not considered an unsafe operation. Unsafe operations come in using pointers, not in creating them. Next, we create a mutable reference, but this time we catch it as a mutable pointer, which hypothetically would allow us to change the data at that address. With our variables set up, we open an unsafe block. Checks will be disabled for all operations within the unsafe section, so we should try to minimize code therein. Within the block, we are accessing the pointers to print the values they store. To do so, like in C or C++, we must dereference the pointers, in other words, access their values rather than the memory addresses they hold. As a result, the original value of 5 is printed via both pointers. In our second example, we begin by creating an array. In this case, a 32-bit signed integer array of 10 entries, which we then assign values of 1 through 10. Next, we create a mutable pointer to the first element in the array. Just after that, we have a very limited unsafe block. In this case, its sole function is to take a pointer and a length, constructing a slice from the two and returning it. We can catch that value in the buffer variable, then print all of the entries to the screen. For those of you wondering if pointer arithmetic is possible, it is indeed, but it utilizes the offset method rather than being directly accessible from standard operators. If you're interested in this, there are details in the Rust documentation. And that concludes my brief introduction to Rust. I hope you found this video helpful. The entire Rust standard library and a myriad of tools are available on the web, so if you want to learn more, make sure to check out the homepage of Rust for more information.